There we go, that should be good. Screen share, and camera. Excellent. Okay, so today's class we're going to have a look at discrete probability. So we've moved on from the fundamentals of probability, and now we're looking at how to handle more specific kinds of probability. Discrete probability, the whole idea behind that is that you're looking at probability scenarios where there are very specific quantities of things. One of the typical examples you could get would be like dice rolls. You can get the numbers 1 through 6 on a dice roll. You can never roll a half or a 3 out of 2 on a dice. There's only the possible numbers 1 through 6. Whereas something like a continuous quantity would be typically like lengths, where you could have a meter long object, or you could have a 1.02 meter object, or if you were more accurate in your recording, you might have 1.02059 whatever recurring number of decimal places. So we're focusing on the former, which is discrete quantities that can only occur in very specific scenarios. The way we typically represent discrete probability is with probability distribution tables, and they look like this, where little x is, well, let's take a step back. The first thing of note would be capital X. Capital X is the stand-in for the particular scenario that you're looking at. It's referred to as the discrete random variable. And so you'll see a set of notation there that says capital X equals little x. What little x is the possible values that capital X could be. So in this particular scenario, there are 4 different outcomes, 0, 1, 2, and 3. For example, if I were picking balls out of a jar and there's a red ball or a blue ball, this could be the number of red balls that I pick out of the jar on 3 consecutive picks. That's what this could potentially represent. So that's little x and all the possibilities there. As far as all the PR statements underneath, those are the individual probabilities of those particular outcomes occurring. So probability capital X equals 0 just means the probability that I drew 0 of those red balls, or whatever color I said initially. Those are the fundamentals around how the table works. There's a few others, namely that all probabilities still have to be between 0 and 1, and the sum of all probabilities in the scenario have to equal 1. So everything in this table has to add up to 1. And lastly, you'll find that complement probabilities are a pretty potent way of handling this kind of thing. Because sometimes you'll be asked to figure out like the probability that x is greater than or equal to 1, whereas it's much easier to just find x equals 0 and then do 1 minus x equals 0. Because then you have to only solve 1 probability rather than 3. Any questions so far? Okay, let's look at how to fill the table. So here's that jar example. We've got 4 white and 6 black balls. 3 are drawn at random with replacement. So basically what that means is I will reach my hand into a jar, I'll look at the ball, I'll note whether it was white or black, then I'll put it back in, shuffle it up before I pick it another 2 times. Was it picking 3 in total? So, as far as setting up the table, since we're drawing it 3 separate times, the number of possible, well, let's see. This one's saying to do it in the context of white balls. So the number of possible white balls you could draw within 3 consecutive draws would be anywhere from 0 to 3. As far as finding each of these individual probabilities, that's where it gets a little bit trickier. So probability x equals 0 simply means that I drew no white balls. To start with, you want to figure out your baseline probabilities of each particular outcome. So if there's 4 white and 6 black, that means we have a total of 10 balls in the jar, and then the probability of any individual color being picked is just going to be proportional to the number of balls that are that color, which is why you've got a 6 out of 10 for black and a 4 out of 10 for white. Obviously you can simplify that fraction. It's more so written that way just so you can see where those numbers came from. So If you draw no white balls, that means you had to have drawn 3 black balls. And so, because this is done in sequence, the multiplication principle applies. You draw the first black ball, then the second, then the third, which is why you're going to have 6 out of 10 multiplied by itself 3 times for a total of 27 out of 125, or as a decimal, that would end up looking like this. And so you put that number in that spot. Any questions so far as to how that came about? Okay. From here, it gets slightly more complicated, although not by much. For probability x equals 1, you've now got to figure out what is the likelihood of drawing specifically one white ball. Now, the part where it's a bit more challenging is that there's multiple combinations that you could have. For example, you could have a white in the first spot, a white in the second spot, or a white in the third spot. And so, because you've got 3 separate possibilities, there's an addition principle that's implied there, which is you add the probabilities of each of those possibilities. But otherwise, you calculate each individual probability the exact same way. White, then black means 4 out of 10, 6 out of 10, 6 out of 10, so on and so forth. What you'll find is that these questions that have with replacement in them, or basically any question where the probabilities don't change from trial to trial, any number of, like, whatever the combination is, still ends up being the exact same multiplication. It doesn't matter which order I do these multiplications in, I get the same result anyway. So you won't have to simplify each of these individually. A lot of the time, if it's a with replacement thing, then you just do the math one time and then just multiply through by the number of possible combinations. So you do 4 out of 10, 6 out of 10, 6 out of 10, and you'd multiply that by 3 because there's 3 copies of that same thing. X equals 2, exact same idea. So this time you've got 2 whites and you can put them in either of those combinations, or the other way to think about it would simply just be to say where the black ball is going to go. And so that's going to end up being the exact same idea. The reason why it's a slightly different probability is because the probability of white is different to the probability of black. So same principle, but because it was different numbers, you get different outcome. And then yeah, capital X equals 3. Well, then you've got all W, so 4 out of 10, 4 out of 10, 4 out of 10. And so you just put those all in the right spots. And a final validation, you might want to add them all up, just making sure that they all add up to 1. That's filling a table. Any questions on that? Okay, now let's look at how to actually use the table. So, a pretty common question is to find the probability over a particular interval. Previously, we were just finding the probabilities of each individual outcome, and so that was just the approach we were looking at earlier. When it comes to using the table, a lot of the time it'll say find a range of probabilities. In this case, probability of capital X being greater than or equal to 2. All that means is you look at all the outcomes that are greater than or equal to 2, and you add all of their probabilities together. That's as far as that ever goes. So you take your 0.288, your 0.064, add them together, get your result. Nothing too crazy. Where it gets slightly harder is what I mentioned at the beginning, which was you can use complement probabilities to solve things that you otherwise wouldn't be able to solve. So let's say this table is fully unknown except for the x equals 0 scenario, and I still want to find x greater than or equal to 1, which means I want to know all of these, but I don't. So what I could do instead is I know this one, this x equals 0 is 0.3, and I know that if everything in here has to add up to 1, then if I subtract 0.3 from 1, I should get whatever all this adds up to giving, which is why you get your 0.7. Any questions on that? Okay, and then lastly, this will be a CAS sort of question usually, although I have given a way you can do it tech-free should you need to. One of the things you might get is a fully, well, not maybe necessarily an unknown probability table, but one that has variables in it. The way you always handle this is you start by making sure that all the probabilities have to add up to 1. So you just put a plus sign between all of these values and then let it equal 1 because probability distribution tables have to add up to 1. From there you can simplify that and you realize you've actually got a quadratic. And so you can solve that however you please. This could have been solved using cross-product method. Quadratic formula is what's posted here. Or otherwise, if it's CAS, obviously, you could just solve. There's no real issues there. That's going to give you 2 possible outcomes, either a fifth or -1. Probabilities have to be positive, so we're going to take P equals a fifth in that one. Now, it's worth specifying. P is not necessarily a probability. It's still a variable. These are probabilities. And so the actual thing you have to watch out for is if I sub in P equals whatever into these spots, these need to all be between 0 and 1 and add up to 1. Both of these will add up to 1 by definition because you've made it equal to 1 to solve the equation. And so really you're just making sure that all of these are between 0 and 1. Now it's pretty obvious why this isn't going to work. It's going to make that one negative. It's going to make that one negative. You're going to have all sorts of issues. But it's worth highlighting that P isn't necessarily a probability. And so if it's written in a really strange way, you might actually have a scenario where a negative P value actually creates positive probabilities. But it'll depend entirely on the question there. They'd have to be all squared, for instance. Something like that. Okay. And then lastly is, lastly is going to be conditional probabilities. So we always solve conditional probabilities the exact same way, or at least we can always solve conditional probabilities the exact same way, which is to start by expanding the conditional probability formula, which means you want the intersection of the two things that are mentioned and then dividing by whatever the conditional is. And in every case, the conditional is going to be whatever's on the right-hand side. So, how intersection works with intervals, the easiest way you can go about that is just draw a little number line. So, x greater than or equal to 1 looks like this. X less than 3 looks like this. And so if you think about the intersection between those, you're just looking at where those both overlap. And that's going to be from between 1 and 2, which is why we can now simplify that numerator as between 1 and 2. From there, we just solve. So between 1 and 2 just means these two things add together, which is why that's there. And then probability of x less than 3, you can either add all of these together, or you can do 1 minus this. Up to you. Because this will be like your regular approach, this would be a complement probabilities approach, which is the one that I've suggested here. Complement probabilities because, well, 2 numbers are better than 3, apparently. But it's up to you. As for simplifying this down to a fraction from these decimals, all you ever do is just keep multiplying by 10 on the top and bottom until they become whole numbers. That's the quickest and easiest way to get it back to a fraction that has whole numbers. Yeah. Anything to clarify there? Okay. Let's try a few. I remember last time I did this lecture, it was me talking for the entire hour because I tried to get through all of this. I think it might be better off if we do some questions on this. Let's see. Where's a good way of... Yeah, question 4 is probably a nice way to start. So we'll do Q4. Let's see. You'll even just do from start to finish there. Q4 all. I'll put that in the chat. I'll open up the phone again. Have a read of what's going on there in Q4, starting with 4a, probability x equals 2. What's going on there and why? Any ideas? Probability x equals 2 for that table? Your thing went green, but I didn't actually hear anything there.
Is it 0.2?
Yeah, okay, 0.2. There we go. Yeah, it is 0.2. Why is it 0.2?
Um, when the table, like the column with table where x is equal to 2, it's the like probability is 0.2.
Yeah, correct. So probability capital X equals 2 just means look at this spot and then look down below it. That is the required probability. Nice. Part B, x less than 2. How do we go about that one? Or even just the final number answer is fine.
0.5.
0.5, yeah. X less than 2 just means anything less than 2, and then you add the two results together. 0.3 and 0.2 makes 0.5. Do a strange one. We'll just jump straight to E on this. Capital X less, does not equal 3. Now, I want you to try and do it in a way where you don't add, just to make it a bit fun.
Is it 0.9?
0.9, yeah. What's the special thing you can do without needing to add?
So like you know how the probability of like x being 3 is 0.1?
Yep,
You can subtract that from like 1 and then you get 0.9.
correct. Yeah. So capital X does not equal 3 means you want all of these other things. And so instead of adding all those up, you know that everything has to add up to 1, so you subtract your 0.1. Nice, giving you a total of 0.9. Sweet, that's that. Question 5's got an interesting little version of this question. There's a whole bunch of k's in there, and it wants to say, what must k be for this to be a valid probability distribution? Q5a. Let's have a think about that.
Chris, is it 1 over 15?
1 over 15 is correct. Yeah. How did you come to that answer?
So I added all the k's together, which is 15k.
Mm-hmm.
And then since all the probabilities like have to equal to 1, you just equate it to 1 and then you divide both sides by 15 and you get k is equal to 1 over 15.
Correct. Yeah, absolutely. So the way you always solve this whenever there's unknowns in a table, kind of like I said in the previous example we had here, whenever there's unknowns, you always start by adding everything up to 1 and then you work from there, which is exactly what he's done. Nice. Okay, that's pretty much it there. The rest of it would be about creating probability tables. So let's go with question 12's got a decent one. So we won't necessarily do any probabilities with it. I just want to know what the table would look like as far as the top row of the table. Let's have a read of question 12 and let's imagine what that top row could possibly be. I'll start writing out the table, or at least a framework for it. And if anyone's having any trouble thinking about that, reminder, what does the top row of the table actually mean in probability distributions? Consider that question first.
Chris, would we have columns of 0, 1, 2, and 3?
0, 1, 2, and 3. Okay, what do 0, 1, 2, and 3 mean? Why'd you choose
Like
those?
the amount of times heads appears in the
The
three
amount of
instances.
times heads appears. Okay, let's see. I like the idea. You would have to define a new variable for it. So what matters here is what y is defined as. And in this case, capital Y is defined as the amount that you win or lose. So even though the amount that you win or lose is associated directly with heads, it's not the thing that's actually being tracked in the table. It's the actual money itself that's being tracked. So like for this example that we had, yeah, this one here, we were told specifically capital X is going to be selecting a white ball. So how many white balls were selected? In this case, we're told $Y is the amount that you win or lose. So instead of having 0, 1, 2, 3, you'd actually have the monetary values of each of those instead. Is it fair enough the nuance on why you'd pick it that way instead?
Yeah, all good.
Sweet. So in this case, it was lose 3. That's one possibility. So minus 3. The other possibility was lose 2. Another possibility was win 1. And then a final possibility, win 3. And then each of these are going to have certain likelihoods of occurring. And what you'll find in one of the next sections is how you can figure out, is this a game you should actually play or not? That'll be in the statistics part of this. I think 11b also has, 11b also has questions on that. I think that can chill for a bit. We'll come to that a bit later. For now, statistics. So what I was sort of saying before is this a good game to play? Well, this is where statistics come into play. You want to know, specifically for that game, you'd want to know the mean, which is the average result. But in this lecture, we'll also have a look at what variance and standard deviation are all about. So, mean. What that means is the expected value, or otherwise referred to as the weighted average value of the data set. So it's every single result weighted by how likely it is to occur. This is the equation for the mean. It looks kind of nasty. Fundamentally, all you're doing is you start with whatever your table is, you multiply the columns by each other, so 0 multiplied by this, 1 multiplied by this, 2 multiplied, 3 multiplied, and then you add all the results together. That's what that actually means. That's this whole statement here. And so yeah, that's what you do. And in this case, for this particular probability table, you get a mean, denoted by the Greek letter mu, as 1.2. That tells you that the average result of this data set is going to be 1.2. So where most of the results are going to lie, which kind of makes sense. If you see this 0.4 here, you can determine that the outcome 1 is going to be the most likely. And then very, very slightly, it's skewed towards the right because you've got 0.216 over here, 0.288, and then a little bit more over here. So it's a bit more heavier weighted on the right-hand side than it is on the left-hand side of this, which is why you get a 1.2 result. Yeah, that's that. Sometimes, yeah, I'll cover this. Sometimes, for whatever reason, they'll chuck in a function in there instead of just solving for e of x. So e of x, by the way, was a stand-in for the mean. Sometimes they'll put an actual function on that capital X variable. All that means is that you apply whatever that function is to the x value before you multiply the probability. So in this case, if you've got 2x plus 3, it means you multiply 0 by 2 and then add 3 and then multiply it by 0.2. That's what this says here. Right? 0 times 2 plus 3, and then multiply by 0.2. Same thing here. Double this, add 3. That's what that is. And then multiply by the probability. Double this, add 3, multiply. Double this, add 3, multiply. That's what that is. This, I believe, shows up like rarely in the textbook and never in an exam. That's why I was debating whether or not to actually bother with it. Never seen this in an exam, but at least you'll be able to solve the textbook question when this comes up. If you don't like that approach, you can also do what's referred to as the linear simplification of it, which means you can take this coefficient out the front like that, and then you can just add the b at the very end. This has a lengthy proof. You can't do this normally for any function. This is just specific to the mean, so don't feel like it's not it's not like how we do derivatives where you can take coefficient out the front. It's a little bit different, because otherwise you'd have to take an a at the front of this as well. So if that's confusing, don't bother with it. Otherwise, if you do, or if you don't mind using this, then it can make this a little bit nicer, because it just means you solve the mean like you always have in the previous example, multiply by whatever a is, and then add b at the end. So in this case, e of x for this particular distribution would be 1.5. You would then double that and then add 3. That's another way of doing it. There are other kinds of scenarios that come up. This one comes up a lot, but never in isolation. It comes up later when you start looking at variance. So I'm kind of shooting what I said in the foot a little bit. This one does come up a fair bit, but because it's already included in another equation that is used a lot. The way this one works is you simply you square the x before you multiply. So in this case, 0 squared multiplied by 0.2. 1 squared multiplied by 0.15, so on and so forth. Any questions about this one or anything so far? All right, that was setting us up for the so-called variance, which has a few different definitions for it. If you can read that, by all means, go ahead. This one's probably a bit nicer to work with, which means you want to find the e of x squared, like I just showed earlier, and then you want to find regular e of x and then square whatever that result is. These two things are very different, and you'll see how that all works. You can ignore that. This is using the first equation. You can see it gets kind of nasty. Like that's a lot to try and do by hand or in a single line. So we'll use this table. What we can do instead is do our regular e of x all squared. So we've done e of x before for this table. This table here is the same thing as this table. Hang on, where is it? Where was it? Oh, I guess I did it here. Yeah, it's the same thing as this table. If you were to do e of x, you end up getting 1.5. So the mean of this one would end up being 1.5. The reason why that matters is because part of this equation is to do that value, e of x, and then square it. So we take that 1.5, square it, that's going to get you 9 on 4. The reason why that works, 1.5 is the same thing as 3 over 2. So 3 squared gets you to 9, 2 squared gets you to 4. From there, you want to find e of x squared, which means you go through and then square all these x values as you multiply them. That gets you the value of 3. From there, you just do a subtraction. 3 minus 9 on 4, and you get your 0.75. Now, what this actually means, this is what's called the variance, which means it's a measure of spread, how far spread out your probabilities are. This kind of probability distribution would have low variance. And the reason why is because a lot of the probability is condensed in one particular outcome, x equals 2. If it was quite equally spread out, then you would have a high variance. So the number would be bigger, basically. Instead of having 0.75, you might have 3, you might have 5. It's really hard to get an idea of scale of variance just by looking at the number, but fundamentally, bigger number means more spread. This we can ignore. This will never show up other than in the book. And then standard deviation. So this will be your favorite little thing for probability, and the reason why is because it's always calculated the exact same way. That equation we just did it for variance. All you do is you just chuck a square root on it, and that becomes your standard deviation. It's a very similar statistic. It's still a measure of spread, although it's a standardized way of doing that. And there's a lengthy description as to why standard deviation is preferred over variance. We'll just sort of leave it at the statement that we typically use standard deviation more than we use variance. And if you want to Google how or why, then that's a nice little rabbit hole for you to walk down. Standard deviation is used in calculating what's referred to as confidence intervals, which tell you the percent likelihood that your outcome is going to fall between plus or minus some number of standard deviations. So remember, standard deviations being a measure of spread. When you plus or minus standard deviation from the middle, it gives you a sort of upper and lower bound of where your outcome is likely to be. It's worth pointing out, this kind of statistic, the confidence interval, really only makes any sense if you have an outcome, or sorry, a scenario that has a lot of different outcomes. You'll see in the example below that there's going to be a very strange result that we get. It's worth pointing out ahead of time, this statistic is really only ever calculated when you have a lot of different outcomes. There's 3 different possible confidence intervals that you could calculate. The 95% confidence interval is the only one that ever gets tested. And that is where you're 95% confident that whatever result you have is going to be between plus or minus 2 standard deviations from the mean. So here's what that looks like. If you want to determine a 95% confidence interval for this, you first need to find its standard deviation. The way you do the standard deviation is by finding the variance and then square rooting it. We already have done all the calculations for this before, so I'm just going to borrow the results that we had from earlier. Once you have all those results, you create your confidence interval equation by having your little x in the middle, the mean on both sides, and then plus or minus 2 times the standard deviation from that. Now, the reason this is a weird result is because it told us that we're 95% confident that our little x result, or capital X result, I should say, it's always a bit weird to say between little x and capital X. Little x is the possible value of capital X. So usually you refer to the variable as capital. But basically it means that x could be anywhere between negative 0.23 and 3.23, and we're 95% confident that it'll fall between those values. Now obviously that's pretty nonsensical. Our number possibilities are only from 0 to 3. So number less than 0, number bigger than 3, it's a bit weird. If this was 20 long, then it would start making a bit more sense. Then the reason this is still in there, despite the weirdness, is because I have seen someone's test has had this on it, and it gave a similarly weird result. And so if your school does something weird like this, you now see that getting a result like this does not mean you did it wrong. It means your teacher didn't care enough to make the table big enough. That, or didn't want you to do a 20 long table, because that would suck. Those are statistics. Any questions on how any of that works? Where are the statistics? Uh-oh, where'd they go? Huh, okay, that's a Unit 3-4 thing specifically. Interesting. All right, I guess there's no questions for it here. No worries then, we'll move on. So, that'll be more so for later. Calculating the things aren't so bad, but okay. Binomials. So the way the binomial distribution works is that it's a special kind of discrete probability. Now, so we've kind of gone from just broad probability terms down to discrete, which is a specific kind of probability, down to binomial, which is a specific kind of discrete probability. So the criteria for binomial is that there's only two possible outcomes for a given trial. So think like heads or tails, 1 or 2, yes or no, that sort of thing. Repeated trials of the experiment are independent. So if you remember from probability fundamentals, independent, how to prove that intersection must be the probability of the two individual outcomes. And the probabilities don't change from trial to trial. Usually these things are pretty closely linked to each other. There are some really niche circumstances where they're not, but yeah, that's the reason why they're separate criteria. There are technical ways of separating those. As far as identifying whether you have binomial from like a question perspective, anytime you have like a with replacement sort of scenario, probably going to be binomial. If they say the word independent in there, probably binomial. If they tell you x is a binomial random variable, that's what that statement means, then yeah, you've got that. And then yeah, anything like that. Very classic example is going to be your coin toss, right? Repeatedly tossing that coin, head or tail, so two possible outcomes, and then probabilities aren't changing from trial to trial. The way we calculate them is with the so-called Bernoulli sequence, where you might recognize at least a certain part of that equation. Out of curiosity, anyone remember what that is? I think we did it on Friday, maybe. But anyway, that's the selections equation from counting methods. Instead of using an R, we've used an X, where X is just going to be the number of things that you're selecting. And there's a bit more going on there. So P is going to be the probability of whatever outcome you want to occur, and N is the number of trials. So if you want to find a specific probability, so in this case it's like coin toss 5 times, I want to figure out what's my likelihood of tossing 4 heads, then number of trials is going to be 5 because you're tossing it 5 times. Little x is going to be 4 because you want 4 successes, and the probability of success P is going to be 0.5 because it's a 50-50 shot of getting ahead. Plug them all in, simplify, and you're good to go. So binomial experiments can be really quickly solved without putting a whole lot of effort into it, rather than having to figure out, oh shit, I've got to toss 4 heads. That could be head, 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 tail. It could be head, head, tail, head, head. You know, all that stuff. You don't have to think about the number of combinations because it's built in to the actual equation itself. The CAS can also do this, by the way, Binom PDF. So that exists on both CASs. Let's explore that. So on the TI Inspire menu, 5 for probability, 5 for distributions, and then all the way at the bottom at A is binomial PDF. So you can just click that and then fill out exactly what we had a look at before, which was number of trials. So you could say 5, probability of success 0.5, and if you want, you can give an X value, or you can actually leave it blank and get every possible X value. So this first result here is for X equals 0, then X equals 1, 2, 3, 4, and then what's hidden is number 5. So if you want to see everything, then you can just print the whole thing out, or you can print out a specific one. Just note that 1 does not mean the first element. 0 would be the first element, which is why you got the 0.156, the second one there, because that's X equals 1. That's X equals 0. That's TI Inspire, and then Casio. Where's the? It's going to be at the bottom here. Let me find my. Damn, I didn't update these. Oh no. Oh well, I'll find it quick enough. I believe it's going to be an interactive, distribution, discrete, binomial, PDF. So you'll click that. They've kind of just done it in the. It's really weird. They call this POS. That means probability of success. By the way, at least they had a little heading on or a subheading underneath it to show you. So the exact same idea would be you'd have your n equals 5, you'd have your probability of success as 0.5, and then your little x, well, let's say it's 1. Hit OK, that'll fill it out, and once again you get that 0.15 result from before. That's Casio. Okay. So that's for specifically x equals 0. For probability of a specific outcome. If we go back to the screen share, you'll see we're having a look at how to handle a range of possible probabilities. So let's say you want to find the probability of tossing one or fewer heads from 5 tosses. This works the exact same way that discrete tables work, in that if you want to do 1 or fewer, it means you want x equals 1 and x equals 0. Anything less than or equal to 1. And so you need to find each of these probabilities. Well, okay, this just means 2 separate Bernoulli sequences. One for x equals 0, one for x equals 1, plug them all in, and then add them together. Because they're separate outcomes. You add the 2 results together. CAS also has this. That's binomial CDF, which was located right below where PDF was. So again, if we go to the handwritten, the document camera, menu 5, 5, and then B for binomial CDF, you'll see it's right below the PDF, like I said, and it's a very similar setup. You give number of trials, you give probability of success, and you give the range of possible outcomes. If you ever want it to be a fraction again, just grab a copy of it and press enter. That'll work out fine. And then for Casio, same thing. If you want, you can even go in here and like literally kill one of the letters there and replace it with a C. That'll work fine as well, but probably still easier to go through and actually have the little setup window so you know where to put what. Because they changed the order of things up a little bit. So like for Casio, you have to do the bound first, then trial, then probability. So this one will be from 0 to 1, and then 5 and 0.5. Oh, right, I put it in here. How funny. Let's fix that. There we go. What did I even write there? Binomial P, binomial CDF. Nice. Anyway, that's that. Yeah, cool. Back to screen share. Actually, yeah, any questions about that so far? Because there is a more complicated version of what we just did, which is how we can use complement probabilities. So you had a nice one, which was less than or equal to 1. That just meant you had to add the x equals 0, the x equals 1. But what if I give a greater than? And what if I don't tell you that n, or what if I don't tell you the upper bound? That's real tough. So, actually no, we'll get to what happens if I don't tell you the upper bound. First, we'll go with a known upper bound. So in this case is the coin being tossed 5 times. Find the probability of tossing 1 or more head. That could be nasty, right? You could be doing x equals 1, x equals 2, 3, 4, 5, add all those together. That works. A lot of effort. And so, kind of like what we did for discrete again, if you want to find 1 or more, you could instead do 1 minus x equals 0, which is what's being produced here. Much easier. This kind of approach you'll need to internalize because it's really important for solving these kind of questions where you don't have a known upper bound. In fact, the n value, that upper bound, is what you're looking to get. You're told P, probability of success is 0.25. You want the number of games, n, and you want to guarantee the probability of winning at least twice is more than 0.9. These are really wordy. Even just saying that out loud sucks, but I did pull this from a book. And so this is the kind of wording you have to be able to decipher. Okay, so the way I like to handle this mostly is I start with just what am I actually solving for, which in this case is n. Cool, that gives me at least something to work with. We want an n out of this. The next thing I look for is what's my probability statement? And in this case, it is probability of winning at least twice. That's the statement there. So I'm like, okay, I know I want to get probability x greater than or equal to 2. That's the thing we care about. That thing has to be greater than 0.9. So eventually I'm going to have some statement for x greater than or equal to 2, and I want it to be greater than or equal to 0.9. Well, technically more than 0.9, but yeah. That gives me something to actually work from. So from here, I think, okay, if I were to do x greater than or equal to 2, I could do 2, 3, 4, 5, 6, and not know where to finish, or I could do my 1 minus x equals 0 and x equals 1, going the opposite direction. From there, you can use Bernoulli sequence to expand each of those individual probabilities out. The n is going to be unknown, the p is known, and x is obviously going to be known because it's the x equals 0, x equals 1 situation. That's going to give you 2 statements there to work with. And so all you do is you plug the x equals 1 and x equals 0 back into the equation they came from, and that gives you a statement that you can work with. Now from here, we want this thing to be greater than 0.9, and so all we're going to do is chuck that into a solve. If you're looking at this and thinking you have to do it by hand, no, it's fine. This is a CAS. Now, here's the thing. The CAS will complain if you don't use an equal sign. It'll just flat out just not give you what you want. So even though, yes, we do want more than 0.9, this is a CAS limitation for we're putting an equal sign, not a mathematical reason. If you put an equal sign there, that's going to give you 2 possible n values. If you remember that n is number of trials, you should immediately disregard the negative because negative trials doesn't make any sense. But weirdly enough, decimal trials also don't work either. And so what we now need to do is figure out, okay, how do I round this? Because if I round it one way, I might increase the probability because I'm doing slightly more trials. And if I round down, I might decrease the probability because I'm doing slightly less trials. If you're ever confused in the actual exam, literally just try both. Try round it down to 14, try round it up to 15, and then just see what each of those probabilities end up being. In pretty much every single case, I've always seen you just round up and that gives you the answer, but if you're ever confused in the actual exam or SAC, just define whatever this whole thing is as its own function, and then see which one of those actually gets me greater than 0.9, and then you just give whatever that rounding should be. That's as complicated as this gets. Fair enough. Anything to clarify there? Other than all of it. Which I can do all of it if you want. Okay. Yeah. So like that's the hardest it'll get. Otherwise, the other stuff isn't so bad. A lot of what you do is using the Bernoulli sequence or using the CAS where possible. That's what 11C is all about, sampling with replacement. Binomial is always going to be a with replacement scenario because you've got those repeated fair trials. So let's take a look at 11C. Yeah, we'll do at least the first question here. This notation here, by the way, is another way of saying the selections equation, NCR. So that just means n equals 6 and r equals x. That's all that means. And so when it says find probability capital X equals 3 using the Bernoulli sequence, using this equation, what do you think? Yeah, what do you think we do? We'll do this one live because it'll be a bit easier to see. All digital. How do we actually begin with that one? All we're going to do is sub in x equals 3 into all those spots. So because you're looking for capital X equals 3, it just means that every x you see in the Bernoulli sequence, you're going to replace with 3. So there was this NCR with an x, it's now going to have a 3 in it. Then we had 0.3 to the x, and then we had 0.7 to the 6 minus x. And then all we're going to do is simplify these. So 6, 3 is the selections equation. So that means n equals 6 and r equals 3. Factorial, 3 factorial. 0.3 to the 3. You can change these to decimals if you want to do them by hand. Oh, sorry, to fractions if you want to do them by hand. Otherwise, these are. I know the book doesn't say to use CAS, but yeah, you'll never have to do this by hand. So you'd have your 3 out of 10, 3, 7 out of 10, also to the 3. This you might have to do by hand, so we'll at least simplify this one. Does anyone remember how we simplify factorials? Or even before factorials, what could we do to simplify this a little bit?
We change 6 minus 3 to just 3 factorial.
Yeah, that's good. 6 factorial on 3 factorial, 3 factorial, and then we'll CAS the rest of that out. That's fine. Where do we go from here? If I said just do 6 factorial for me, how do you do that?
6 times 5 times 4 times 3 times 2 times 1.
Yeah, there we go. So what we're going to do is we're going to expand all of these out. We're not going to actually do that multiplication until we need to, but we are going to expand it out. And the reason why, you can put the 1 there if you want, but multiply by 1 doesn't really do anything. The reason why we're going to expand all these out is because it allows us to very easily see what we can cross out and what we can't. And so obviously the 1s can all disappear. We can cut out a pair of 2s, you can cut out a pair of 3s. Yeah, that looks like about it. This obviously will condense down a little bit. So you can cut one of these and make this a 2. And then yeah, so now you got 2, 5, and then that cancels out as well actually. Because 3 and 2 makes 6, so that gets that. Which just gets us to 10. 5, oh sorry, not 10, what am I saying? 5 and 4, 20. And so that would be your coefficient at the front, 20, which basically tells you there's 20 combinations 20 ways that you can choose 3 things from 6 things. That's all that means. And so that gives you a number of, kind of like how we had like W, W, B, W, B, W. We wanted to have all these combinations. That's what this is handling. And then the actual probabilities of each of them are handled over here, which you can cas out. And so yeah, what they'll end up looking like is we had 0.3 to the 3, we had 0.7, which was also to the 3, and then multiply that by the, oops, not plus, but multiply by the 20. That's going to give you a probability of 0.185, so on. And as I said, wouldn't be really expected to do that by hand, although you technically could. It would just take a little bit of effort for the simplifying of fractions. That's binomial. Well, that's at least how you use the Bernoulli sequence. That's already, when it's already given to you. The next thing we'll look at is how to create our own one. But before that, do I need to clarify anything from that example? Okay, so with that in mind, I'll just quickly hit on the 3 things you need for Bernoulli sequence. Actually, I think you only really need 2. You need to know what n is, and you need to know what p is. A little x will depend on the actual question itself. So if you have a read of question 4, so I'll put that in the chat, Q4, what's n and what's p? You might have to read part A as well. So in that case, yeah, if we're going to do part A, we'll look at little x as well. Reminder that n is the number of trials, so the number of times you repeat the experiment. P is the probability of a success, whatever that means in this case, and x is the number of successes that you want. So when I say n is number of trials, what's the thing that we're repeating over and over again? All right, I'll just finish this one off. So it's all about rainfall, and if you look at part A, it's saying what's the probability rain will fall on the first 3 days of a week, but not the other 4. So the thing that's happening over and over again is the days, right? We're going through all the days of a week, of which there are 7. And so that means n is going to be 7. We have 7 total trials that we're looking at. In this case, we're looking for probability of rain, so rain will be considered a success. So in this case, probability of rain, 0.35, which is why P is 0.35. And then lastly, little x will be completely dependent on what's going on here. First 3 days, that's a little bit challenging because now you don't really use Bernoulli sequence for that. I'll talk about that in a little bit. More so this you would use it on, exactly 3. If you don't care when those 3 days fall, then that's when you would use Bernoulli sequence. The reason why you wouldn't be able to use it for this one here is because Bernoulli sequence basically requires no order to matter. If you had to do this way, what you would have to do instead would be rain, 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 no rain, no rain, no rain, no rain. So you'd have 0.35 power of 3, because that's the chance of rain. And then the opposite of that, 1 minus 0.35, that will go power of 4, because that's all the non-rains. There's no binomial coefficient at the front because you don't care about, you only want one specific order. Does it make sense why all the 2 different approaches that, and why you'd use one versus the other? You can stick around and I'll clarify more. Otherwise, that's the last thing I'll say for the lesson.